So here's another example. This is what I might call like a difficult example. So this has, spoiler alert, a total of 3 transformations on it. So either table method or graphing each step, you're going to have 4 individual parts that you do, the original and then each transformation. To me, that's sufficient. Anything beyond that, I think, is unnecessary for determining whether or not you can actually do the transformation technique. So let's go ahead and do this one. So this is big F of x is 3 times x minus 2 quantity cubed plus 1. So from the 4 functions that are in my library, I've got x squared, x cubed, root x, and absolute value. This one most resembles x cubed because it's got the cube. So that means this shape is going to be this, squiggle shape. All right. For shifts, I'm looking for adding and subtracting. So I add and subtract. I have a -2 and a +1. The -2 is inside of my cube. It happens in the parentheses. So that means it changes x and it is going to be horizontal. So I do a horizontal shift. Horizontal stuff is always the opposite. So subtraction actually moves it to the right. So this is going to be 2 to the right because I'm going to have to make all of my x's bigger so that when I subtract 2, they're back to where they started, right? If I want 0 in here, I need 2 minus 2 gives me 0. Okay, I also have a +1. This is not inside the parenthesis, this is outside. So it changes y values, which means it's vertical. So shift by 1 and it moves up. All right, so that takes care of those 2 things. Stretches, I'm looking for multiplication. So I multiply a 3 here, and it's on the outside, so it's a vertical stretch. Now reflections. Reflections are multiplying by negatives. So I do not have any negative multiplication here, so this is an A. If I had like a -3 here, I'd have a stretch and also reflection. The stretch is just like how much it grows by, the reflection is just the negative. Okay, so let's look at doing this step by step. So I've got the base and then 1, 2, 3 transformations, so I'm going to need 3 colors. And I'm still going to do the final answer in the light blue. Okay. So x cubed then my order of operations says I basically have to do it in the order I've listed here. And in HAWX, they list these things for you. You don't have to remember the order. Okay, so horizontal shift is next. So I have to pick up each point and move it 2 to the right. So 1, 2, 1, 2, 1, 2. Okay. So that is x minus 2 cubed. All right, next is a stretch of 3. So vertical stretch. A vertical stretch doesn't move. It's just growing it. It's like a spring, basically. So the center of my spring is still at the same spot. It's just gotten longer on the top and bottom. All right, so instead of, and just like this operation is multiplication, it's multiplication in my graph. So 1 times 3 is 3. 0 times 3 is 0. -1 times 3 is -3. Okay, and this is 3x minus 2 cubed. And then the last one is our vertical shift up 1. Oh, by the way, the vertical distance between these points is 1 square, right? Here the vertical distance is 3. That's the thing that tells me I had a vertical stretch of some kind. They are no longer 1 square apart. They're now 3 squares apart. So that is the factor that I would multiply by. Okay, so now vertical shift up 1, up 1, up 1. All right, final answer is this blue. It doesn't look great, I will confess. However, that's one reason that it's really nice to have the anchor points and like do the table technique. Okay, so x cubed. So I start with my anchor, then I do a shift to the right 2, a vertical stretch by 3, and then a vertical shift up 1. And I've actually decided to put a grid down here to show you what your answer would look like if you just do the table. So if you do one at a time, you know, have each of them and then you just label which one's correct. So this is the 3x minus 2q plus 1. Okay. So x cubed, remember our anchors are usually negative 1, 0, 1. Still true in this case. All right. Negative 1, 0, negative 1, negative 1, 0, 0, 1, 1. Shifting to the right 2. All right, so it's horizontal, which means y stays the same. And I'm going to add 2 to each x value because that's going to move it to the right. This is something that confuses students. So up here I have subtraction, but then down here I have addition. That's because I have to increase all my x's so that when I plug them back here into my cube, the subtraction goes away because I would get x plus 2 minus 2 is just x, right? Okay, so increase each by 2, y stays the same. Add 2 to x, y stays the same. Add 2 to x, y stays the same. And if you look, by the way, this was our pink function. Yeah, our pink function. So those are the same points that I have calculated here. Vertical stretch by 3, that means, because it's vertical, x stays the same, y you multiply by 3. X stays the same, y multiply by 3, x stays the same, I dropped a negative, there we go, y multiplied by 3, x stays the same, y multiply by 3. Okay, finally, vertical shift up 1. X stays the same, add 1 to y. 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 So if you do the table technique, all of your work is done within the table and you only have to graph this last step. So the 3 points I'm going to graph will be negative 1, negative 2, 2, 1, and 3, 4. Which admittedly looks a lot better than the one above. All right, so I get this. It's up to you which technique you like to use. If there's only a few transformations, I feel like this isn't that bad. But the more transformations you get, the harder it can be to see what it is you're doing. And for that reason, having that table can be really helpful.